Namaskar. Welcome to the session on technology of milk. Milk is secreted by all the species of mammals to feed nutrition to their young ones. It also provides immunological properties to the feeding babies. Milk is a dilute emulsion of milk fat combined with colloidal dispersion of proteins with a continuous phase of solution containing lactose minerals and other water-soluble solids. In the milk processing industry, the measurement of the physical properties of the milk and milk products are important for designing of the processing equipments, that is heat conductivity, viscosity, to determine the concentration of components, that is specific gravity, freezing point to determine added water, or to assess the extent of a chemical or physical change, that is titrable acidity to know the microbiological changes, or viscosity to assess the aggregation of protein micelles or fat globules. Some of the properties such as color and taste also plays important role in accepting and grading of milk before it is processed. Let's learn about the physical properties of milk under the following sections: color and taste, pH and buffering capacity, refractive index, viscosity, surface tension, freezing and boiling point, specific heat, electrical conductivity, oxidation reduction, that is redox system, and lactose and its significance in the dairy industry. Now, first coming to color and taste. The white color of milk is due to the scattering of visible light rays by casein micelles and fat globules. The yellow color of cow's milk is due to the presence of yellow colored pigments, that is carotenes, while the buffalo milk looks whiter due to absence of this component. Homogenization of milk results in a whiter product due to increased scattering of light by smaller homogenized fat globules. The serum phase of milk is greenish due to the presence of riboflavin, which is responsible for the characteristic color of whey, fox and McSweeney. Taste. The taste of the milk is generally a part of flavor. Flavor is defined as the combination of taste and smell. The taste of the milk is both sweet and salty. The sweet taste is contributed mainly from the lactose content, while the salt taste is due to the salts present in the milk. The human milk tastes sweeter than cow milk due to the presence of higher percentage of lactose in the milk. The fat is the component which contributes to the rich flavor of the milk. Higher the fat, richer the flavor of milk. pH and buffering capacity. The pH of milk usually ranges between 6.5 to 6.7 with a mean value of 6.6. An important characteristic of milk is its buffering capacity, that is resistance to changes in pH on addition of acid or alkali. Milk contains a range of groups which are effective in buffering over a wide pH range. The principal buffering compounds in milk are its salts, particularly soluble calcium phosphate, citrate and bicarbonate, and acidic and basic amino acid side chains on proteins, particularly of caseins. The buffering capacity of milk is estimated by determining its titrable acidity, which involves titrating a sample of milk containing a suitable indicator, that is phenolphthalein, with sodium hydroxide, and thus is a measure of the buffering capacity of the milk between its natural pH and the phenolphthalein endpoint. Calcium and magnesium influence the titration curves of milk because as the pH is raised, they precipitate as colloidal phosphates, and as the pH is lowered, the colloidal calcium and magnesium phosphates are solubilized. The casein and phosphates account for the major part of the titrable acidity of fresh milk. The increase in titrable acidity in stored milk is due to activity of the microorganisms which converts lactose to lactic acid. The acid-base equilibrium in milk is influenced by processing operations. Pasteurization causes some change in pH due to loss of carbon dioxide and precipitation of calcium phosphate. Higher heat treatments such as sterilization result in decrease in pH due to degradation of lactose to various organic acids, especially formic acid. Refractive index. The refractive index of milk at 20 degrees Celsius is normally in the range of 1.3440 to 1.3485. The refractive index of milk and its total solids content varies with changes in the concentration and composition of the solutes in the milk. Milk contains many dissolved components and fat in emulsion form and proteins in colloidal form. The milk absorbs light of wide range of wavelengths and also scatters UV and visible lights due to presence of proteins. Milk absorbs light of wavelengths between 200 and 380 nanometer due to the presence of proteins and between 400 and 520 due to the presence of fat globule particles. Scattering of light by the globular fat particles present in milk has been used to estimate its fat content. The commercial milk scanners have been developed by using this principle. Viscosity. The unit commonly used for measuring viscosity of milk is the centipoises, that is 10 raised to minus 2 poise. The viscosity of milk and dairy products depends upon the temperature and on the amount and state of the dispersion of solid components. Representative values at 20 degrees Celsius are whey 1.2 centipoise, CP skim milk 1.5 CP and whole milk 2 CP. From these values, it is evident that the caseinate micelles and the fat globules are the most important contribute to the viscosity. Important factors that influence the viscosity of milk are state and concentration of protein, state and concentration of fat, temperature of milk and age of the milk. Coming to the first one, which is state and concentration of the protein. The viscosity of colloidal systems depends upon the volume occupied by the colloidal particles. Changes in the caseinate micelles produced by either raising or lowering the pH results in increased viscosity. The viscosity is approximately doubled by the addition of 10 ml of 1.4 to 3.8 normal ammonia to 90 ml milk. Addition of alkali, pH up to 11.7, urea up to 4.8 molar and calcium complexing agents to concentrated 22.7% solids, skim milk causes a marked transient increase of several folds in viscosity followed by a sharp decline. This is due to the swelling of the micelles followed by their disintegration. Now, next is the state and concentration of fat. Viscosity increases with increasing concentration of fat and solids, not fat, but consistent general relationship could not be established. Homogenization increased the viscosity of the milk due to increase in number of fat globules in the milk. Temperature. The viscosity of milk and dairy products depends upon the temperature and on the amount and state of dispersion of the solid components. Cooling increases viscosity due to the increased volume of casein micelle, and temperatures above 65 degrees Celsius increase viscosity due to the denaturation of whey proteins. Cooled raw milk and cream exhibit non-Newtonian behavior in which the viscosity is dependent on the shear rate. Agitation may cause partial coalescence of the fat globules, that is partial churning, which increases viscosity. Fat globules that have undergone cold agglutination may be dispersed due to agitation, causing a decrease in viscosity. Surface tension. The surface tension of milk varies between 40 and 60 Newton per meter, with an average of about 52 Newton per meter. The surface tension of whole milk and skim milk decreases with increase in temperature. It also varies with the age of the milk. The surface tension of rennet whey, skim milk and cream are reported to be 51 to 52, 52 to 52.5 and 42 to 54 respectively. The principal surfactant skim milk are proteins, phospholipids, mono and diglycerides. The soluble solids such as salts and lactose does not contribute significantly to the surface tension. Hence, the skim milk and whey have higher surface tension and cream has lower values. The surface tension decreases with increase in fat content of milk. Boiling point. Boiling point of a solution is the temperature at which the vapor pressure of the liquid equals to the external, that is atmospheric pressure. The water content in fluid milk is highest and hence the boiling point of milk will be close to that of water. But being a colligative property, it is influenced by the dissolved substances like lactose, minerals, etc. and hence it is slightly higher than that of water. Since the vapor pressure of a solution is always less than the vapor pressure of the pure solvent, it follows that the boiling point of a solution will always be higher than that of the pure solvent. Pure water boils at 100 degrees Celsius, while the boiling point of normal milk is 100.15 degrees Celsius. Milk constituents are responsible for the elevation of the boiling point of milk. The normal ionic molecular colloidal equilibrium is altered due to heating. Addition of water lowers the concentration of dissolved substances responsible for the reduction in the boiling point. As such, adulterated milk with water boils at a lower temperature than the normal milk. Freezing point. The freezing point of milk, like that of any other aqueous system, depends on the concentration of water-soluble components. The average freezing point of bovine milk is usually within the range minus 0.512 to minus 0.550 degrees Celsius. The average value for cow milk is close to minus 0.522 degrees Celsius, buffalo milk minus 0.560 degrees Celsius, sheep milk minus 588 degrees Celsius and goat milk minus 0.575 degrees Celsius. Freezing point depression of milk is inversely proportional to the souring of milk, fortification of milk with lactose or non-fat solids or addition of sugar will increase the depression of the freezing point. Amount of water added decreases the freezing point depression. Colostrum is having a freezing point of minus 0.605 degrees Celsius, which is slightly less than normal milk due to the presence of more soluble milk solids. The composition of milk is altered by the other diseases like mastitis, but in order to maintain the osmotic pressure in equilibrium with blood, the lowering of the lactose content is compensated by increase in the sodium chloride. As such, the milk obtained from the animal affected with mastitis will not alter the freezing point. The freezing point is a property controlled by the number of particles rather than the kinds of particles in the solvent. The major components affecting the freezing point are lactose and soluble salts. 75 to 80% of the depression of the freezing point is due to these two constituents. Fat, protein, colloidal calcium phosphate, casein colloids and fat globules have negligible effect on the freezing point of milk because of their high molecular weight. Specific heat. The heat capacity of a substance is the quantity of heat required to raise the temperature of a unit mass through a unit range. The term specific heat is used almost interchangeably with the heat capacity. It is the ratio of heat capacity to that of water at 15 degrees Celsius, that is 0.99976 calorie per gram per cm cube. and thus it is dimensionless. The numerical value of specific heat is nearly the same as that of heat capacity. Skim milk exhibits a small but definite linear increase in heat capacity between 1 and 50 degrees Celsius from about 0.954 calorie GC. There is marked decrease in heat capacity as the total solids content of the sample is increased. Dried skim milk products have heat capacity of 0.28 to 0.32 calories GC in the 18 to 30 degrees Celsius temperature range. The heat capacity of milk fat in either solid or liquid state is about 0.52 calorie GC and its latent heat of fusion is about 20 calories per gram. Thus, the heat capacity of the cream depends on the fat content in the cream. Electrical conductivity. The specific conductance of cow's milk reflecting its concentration and activity of ions is on the order of 0.005 ohm Cm-1 at 25 degrees Celsius. Most normal samples fall in the range of 0.0040 to 0.0050 ohm to the power minus 1 Cm to the power minus 1. Higher values usually represent mastitic infections which increase the concentration of sodium and chloride in the milk. Measurement of electrical conductivity has been used for rapid detection of subclinical mastitis disease in milking animals. The sodium, potassium and chlorides ions of milk are the greatest contributors to its electrical conductivity since they are present in the highest concentration. The fat globules in milk reduce the mobility of ion and hence the conductivity of whole milk is less than that of skim milk. The production of acid due to bacterial activity increases the conductivity. Oxidation reduction, that is redox system in milk. The oxidation reduction reactions involve transfer of electrons between atoms or molecules. Transfer of oxygen, that is O, or hydrogen H, or both may also occur. Oxidation is loss of electrons while reduction is the gain of electrons. In a redox system, when half of the system is having oxidation reaction and the other half is having a reduction reaction, there will be no flow of electrons either into the system or go out of the system. In normal milk, there are several complicated biological systems with varying composition and concentration. In addition to this microorganism, gaining entry into milk contributes certain redox systems to it depending upon the type of the organism. Reduction of redox indicators such as risazurin, methylene blue are generally used as an index of the bacterial quality of milk by measuring the reduction time at a suitable temperature of milk containing the dye. Methylene blue is reduced by freshly drawn milk when it is drawn from udder anaerobically, indicating a more negative potential than methylene blue system. Exposure to oxygen will change this potential to be more positive than the methylene blue system. Apart from this, the chief oxidation and reduction systems present in milk are ascorbate, lactate and riboflavin. The concentration of dissolved oxygen is the principal factor affecting the redox potential of milk. Milk is essentially free from oxygen when secreted, but in equilibrium with air, its oxygen content is about 0.3 millimolar. Lactose. Lactose is the carbohydrate which is present in milk of all mammals. It is a disaccharide consisting of glucose and galactose. Its concentration varies widely between the species but almost constant in a particular species. Lactose content in cow's milk varies between 4.8 to 5.0, while that in human milk varies between 6.5 to 6.7%. Lactose plays an important role in milk and milk products. It is an essential constituent in the production of fermented dairy foods. It affects the texture of the certain concentrated milk products such as sweetened condensed milk and frozen dairy products, and also indigenous dairy products such as Koa. It also plays a vital role in heat-induced non-enzymatic browning reactions, which not only contributes to the color but also to the flavor of the products. Milk products are especially sensitive to the effects of heat treatment encountered under conventional process and storage conditions because of an abundance of reactive functional groups, that is aldehyde group of lactose, sigma amino group of lysine, and other reactive nitrogen containing groups, for example, indole group of tryptophan, imidazole group of histidine, guanidine group of arginine, and the alpha amino group of proteins and free amino acids. The most important heat-induced changes in dairy products that involve lactose are the changes associated with browning. Milk is the only important naturally occurring protein food with a high content of reducing sugars. Lactose may isomerize or it may react with protein in milk. The reaction of lactose with the caseins and whey proteins of milk systems will be via Maillard or non-enzymatic browning reaction. It is also referred to as glycosylation of proteins. For example, in case of lactose, it is known as lactosylation of proteins. Maillard type browning. Generally, Maillard types browning is detrimental to the organoleptic, nutritional and functional qualities of the product and are therefore undesirable. However, this reaction is being utilized favorably in the preparation of products like Koa, where milk is heated in the presence of sucrose to produce brown product with a pleasant flavor. Maillard reaction also plays an important role to the generation of flavor during the manufacture of ghee or clarified butter and milk chocolate. Factors that influence Maillard reactions. The overall rate and product profile of Maillard reaction in foods are highly dependent on number of parameters. However, the most important are listed below: reactants, pH, temperature, moisture content, water activity. Caramelization is a type of non-amino browning reaction. This process consists of heating sugar slowly to around 170 degrees Celsius. As the carbohydrates are heated, the molecules break down and reform into compounds with a characteristic brown color and flavor. It is a chemical decomposition of non-protein substances that occurs spontaneously at high temperatures, and the reaction is known as pyrolysis. Caramelization is a complex, poorly understood process that produces hundreds of chemical products. Caramelization by heat during baking contributes to flavor and color. However, it occurs to limited extent in milk and milk products and hence has limited significance. Caramelization is the removal of water from a sugar by heating. This process results in isomerization and polymerization of the sugars into various high molecular weight compounds. Compounds such as difructose anhydride may be created from the monosaccharides after water loss. The fragmentation reaction of sugars during heating would result in low molecular weight compounds that may be volatile and may contribute to flavor. Polymerization reactions lead to large molecular weight compounds that contribute to the dark brown color. Caramelization type of browning may be defined as the heat decomposition of sugars as a function of pH and buffers in the absence of amino compounds. It requires high order of activational energy. Caramelization is the oxidation of sugar by heating, resulting in the production of nutty flavor and changing to brown color. During the process, volatile chemicals are released, producing the characteristic caramel flavor. Conclusion: milk is a mixture of soluble colloidal and emulsion substances distributed in aqueous medium. The physical properties such as thermal conductivity and viscosity are important in designing and operation of the equipments. This property is widely used to detect the subclinical mastitis disease in animals. Elevation of freezing point can be used as an indirect method of detection of adulteration of milk with water. The principle of refractive index is used in development of Milko scanner for instant detection of fat in milk. Milk contains a range of groups which are effective in buffering over a wide pH range. The principal buffering compounds in milk are its salts and acidic and basic amino acid side chains on proteins. Lactose is a disaccharide present only in mammalian milk. It plays an important role in production of fermented milk products. It is also responsible for textural changes in concentrated milks and frozen dairy products. Lactose is the major contributing factor in non-enzymatic browning reaction in the dairy and milk-based foods. Thank you.